So, in this unit, we're going to be talking a lot about heat. It's important to understand what we mean when we say heat. Heat is a type of energy, and there are many types of energy that you can see in the diagram on the right. What all energy has in common is that energy can be used to do work. So, work could be a form of movement. Work could also be the ability to change something. We say that heat is a type of kinetic energy because it involves movement. So, one major class of energy is called kinetic energy, and all forms of kinetic energy involve movement. Heat or thermal energy involves the movement of particles. As they gain heat energy, the particles start to move faster. As they lose heat energy, the particles start to move slower. So you can observe the amount of heat energy something has based on how quickly the particles are moving. Other types of kinetic energy are general motion, like moving on a bicycle or a ball rolling down a hill, electricity, because it involves the movement of electrons, sound and light, because they involve the movement of waves. And so these are all different types of energy that we're going to be thinking about as we talk about what happens to the heat energy that we use. But there's another type of energy, and that's called potential energy. Potential energy is a stored type of energy. So, for example, if you lift an object off the ground, you give it potential energy. That would specifically be gravitational energy, because when you let go of that object, gravity is going to pull it back to the earth, and that movement is when it's transformed into kinetic energy. So potential energy is a form of stored energy that is often transformed into the energy of movement, which is kinetic energy. Some other examples of stored or potential energy include elastic energy. So that's when you squeeze a spring or pull a rubber band, you're giving it potential energy so that when you let it go, it can move. Chemical energy, like the energy found in batteries and also found in food, that comes from the bonds between the molecules or particles that are in those batteries or food. When bonds are made, usually energy is released. When bonds are broken, usually energy is absorbed. And then also things like fuel, when you burn wood or gasoline, that's another good example of chemical energy because it's the bonds being rearranged in those substances that results in energy being released. The one at the top here that says electric potential energy describes the electric attraction between positive and negative particles. So when we talk about the attraction between particles, a lot of times that attraction results from positive and negative charges that we're going to study later in this year. So we know that energy can be released when particles are rearranged. Energy can be absorbed in this process. Fuel or food is a good example of stored chemical energy. When fuel is burned in the presence of oxygen, that stored potential energy can be transformed into heat, which we now know is a type of kinetic energy. So when we think about energy, we don't want to think about energy being created or destroyed. We want to think about energy being transformed between these different types that I've described. The first law of thermodynamics, sometimes also called the law of conservation of energy, talks about this idea. Energy can neither be created nor destroyed. It's only converted or transformed from one form to another. But as we use energy, it does become spread out and less useful. So we could say that energy dissipates or becomes spread out rather than saying that energy is destroyed. The quantity of energy is still the same. It's just that it's harder to use, and so we would say the quality of the energy is different. For example, when you eat food, that energy is converted into movement. And when you move your muscles, you're able to do work, right? Movement. However, the energy, as it is converted into movement, also releases thermal energy or heat, which is why your body gets warmer as you exercise. And that thermal energy is released into your environment. So it may seem like you're losing that energy, but really it's just being transformed into heat energy. And technically that heat energy could be used for another process, right? That could change something else in your environment. Sometimes people used to talk about the butterfly effect, the fact that even very small things that happen around us can affect other things or other people in small ways, and that all those small changes can add up. And that is true. Another example would be this energy efficient light bulb. So, light bulbs can have different levels of efficiency. And what we're talking about there is the amount of energy that goes in that's actually used to produce light. So all the energy that goes into the light bulb must come out of the light bulb, but not all of that energy comes out as light. Some of it comes out as heat, for example. Some of it is lost through the conduction of the wires, but it's not really lost. It's just also released as heat that's not able to be completely isolated or conserved inside those insulated wires. As light bulbs have gotten more efficient, they've often also gotten cooler, right? So they're cool to the touch. And that's one way that we know they're more efficient, because they're not dissipating or releasing heat into the environment, because that's not their purpose, right? And that makes them less efficient if they're releasing energy in a form other than light. Our final example will come from biology. In biology, or maybe environmental science, you talk about food webs. And a food web is a good example of how energy moves through the environment. Remember that energy starts with the sun, and that producers are the living things that can usually absorb energy from the sun and use it to create chemical energy through photosynthesis. So these producers use energy from the sun to create sugar, for example, and oxygen through a process called photosynthesis. And then consumers get their energy by eating the producers. But what's important to notice in this food web is that there are some arrows showing that in each level of the food web, some of the energy does go out into the environment in the form of heat. And that's probably the most common way that energy sort of becomes misplaced or harder to notice, is just when it dissipates into the environment as heat. And that can happen anytime we're exercising, moving, building, or repairing cells, for example. Here's an example of the decomposers getting energy from the consumers, but again, even the decomposers lose some energy to the environment, or it is transformed to heat energy, and it's harder to notice. So that happens at every step in the food web, but it's not necessary that energy is always conserved within a small system like this one, because most systems are open systems. It's just important that energy is conserved in the universe. And notice that a lot of our energy comes from the sun, right, which doesn't originate on Earth, but originates in our solar system.